Hey everyone, welcome to the Explainer. Alternating current can look like total chaos at first glance, right? But today, we're going to take that chaos and distill it down into clear, undeniable math. If you're an engineering student trying to finally wrap your head around AC waveforms, you are absolutely in the right place. We're going to break down the maximum, instantaneous, average, and RMS values and make it all super simple. Let's get into it.
So here's the million-dollar question. How do you actually measure a moving target? I mean, direct current is easy. It's just a nice, predictable, flat line of continuous voltage. But alternating current? It's a wave. It is constantly flipping direction. It ramps up from zero to a positive peak, drops back to zero, plunges to a negative peak, and then does the whole shebang all over again. This shape-shifting raises a huge question for us. What is your multimeter actually reading when the value literally isn't the same from 1 millisecond to the next?
Just look at this classic sine wave right here. It perfectly captures our dilemma. Because it's constantly on the move, we can't just guess at the math. We really need to introduce a baseline anchor, a definitive point of reference that we can tie every single other measurement back to. Because without that anchor, honestly, we're just looking at a squiggly line.
All right, let's establish that anchor. We call it the maximum value, usually written as Vm for voltage or Im for current. Now, this maximum value, it is the absolute boss of the wave. It's the highest peak amplitude the wave ever hits during its cycle. And why is this so crucial? Well, as we go through this explainer, you're going to notice a pattern. Literally every other useful number we calculate is just going to be a fraction, a percentage, or a specific snapshot of this main boss value.
Speaking of snapshots, what if you don't actually care about the big picture for a second? What if you want to, pause time and look at the exact value of the wave at one tiny fraction of a millisecond? Well, for that, you use the instantaneous value. Our textbook sources give us this really elegant standard equation, E equals Em sine omega t. This is literally how you freeze an AC wave in its tracks to see exactly what it's up to at a specific instant.
And what's wild is how simple the math actually is when you look under the hood. That lowercase e or I, that's your instantaneous snapshot. The uppercase Em or Im, that's our anchor, the boss maximum value we just nailed down. And that sine of omega t is just the changing time angle, which you'll sometimes see written as theta. Notice how the instantaneous value totally depends on taking that maximum peak and multiplying it by the sine of whatever angle the wave happens to be at. Like I said, it always comes right back to the boss.
All right, so we know the peak and we know how to grab a snapshot. But how do we summarize the wave's overall effort over time? Well, in electrical engineering, we've got two main ways to tackle this. First, we have the average value, which tells us the steady current that would transfer the exact same electrical charge as our AC wave. And second, we have the RMS value, which is the steady direct current that would produce the exact same heat power. So charge versus heat. Let's look at the average value first. But watch out, because there's a massive mathematical trap here. If you've got a standard symmetrical AC sine wave, the positive half of the wave is a perfect mirror image of the negative half. So if you try to average out a full, complete cycle, the positive and negative just cancel each other out entirely, leaving you with a big, fat zero. And zero is completely useless to us when we're trying to figure out charge transfer. So to get around this, for symmetrical waves, we strictly calculate the average value over just a half cycle. So what does that half cycle average actually come out to? It boils down to a magic number, 0.637. When you integrate the instantaneous values over that half cycle, the math simplifies beautifully. To find your average value, all you do is take your maximum peak and multiply it by 0.637. That's literally it. I.AV equals 0.637 times Im. And boom, you have your equivalent charge transfer. But let's be real for a second. Out in the field, we usually care way more about the actual work being done, specifically heat and power transfer, than we do about just charge transfer. Take a look at how a power wave fluctuates. Because power is proportional to the square of the current, even the negative half of a current wave still produces positive heat. And this brings us to the absolute MVP of AC measurements, the RMS value. RMS stands for root mean square. Honestly, just think of RMS as AC's DC alter ego. It's the absolute industry standard. By definition, the RMS value is the specific amount of alternating current that would heat up a resistor by the exact same amount as a steady DC battery over the same time. Whenever you grab a standard multimeter to read AC, it is inherently designed to give you this RMS value, because heat-producing capability is what practically matters most in the real world.
And just like with the average value, calculating RMS for a symmetrical sine wave comes down to a super simple constant. Through the math of squaring the wave, finding the mean, and taking the square root, we end up with 1 over the square root of 2, which gives us 0.707. So to find the RMS value, you just take your maximum value and multiply it by 0.707. Once again, everything ties right back to that peak anchor. IRMS equals 0.707 times IM.
Now, what if you're working on a problem and you need to relate that heat equivalent directly to the charge equivalent? Engineers use a really handy ratio for this called the form factor. It's strictly defined as the RMS value divided by the average value. So, if you divide our two constants, 0.707 by 0.637, you get exactly 1.11. For a pure sine wave, the form factor is always going to be 1.11. It's just a really quick, reliable way to check the shape and efficiency of the wave you're dealing with.
Okay, let's bring the whole shebang together. Consider this your ultimate exam cheat sheet. Seriously, screenshot this one. Notice how every single one of these useful metrics, the instantaneous snapshot, the average charge equivalent, and the RMS heat equivalent, is just a basic multiplication of the maximum value, IM. Once you know the absolute peak of your wave, you can basically decode everything else about it using just these simple constants.
So I want to leave you with this one thought to really let everything sink in. Next time you look at a wall outlet or the back of an appliance and it says 230 volts AC, are you looking at the actual peak of the wave or its DC alter ego? Based on what we just covered, almost every voltage rating you see in daily life is actually the RMS value, which means if the RMS is 230, that hidden maximum peak pulsing through the wire is actually way, way higher. How much higher? Well, you've got the formula now. I'll let you do the math. Thanks for hanging out with me for this explainer. Keep asking questions and keep decoding the engineering world around you.